For decades, the command line was a reactive environment. A human typed a command, pressed enter, read the text output, and typed the next command. The terminal itself was a passive canvas, waiting for sequential instructions from a single operator. Today, developers routinely deploy autonomous coding agents like Claude Code or Codex that do not wait for keystrokes. A single user might dispatch one agent to write tests, another to bisect a regression, and a third to refactor a service, all running in parallel across different branches. Scaling up to 5 or 6 concurrent agents quickly hits a cognitive breaking point. Keeping track of which task belongs to which agent, or remembering where a specific background process was left, leads to a state of mental exhaustion known as context rot. Standard terminal environments have no internal map of the tools running inside them. Because they lack semantic awareness of an agent's execution state, they cannot alert a developer when a background process hits a permission blocker or finishes a task. Effectively managing parallel algorithms requires a terminal architecture engineered specifically for asynchronous supervision, rather than the synchronous typing of the past. Modern block-based terminals often rely on Electron or web wrappers. These frameworks carry significant memory and CPU overhead just to maintain the basic interface. When an interface consumes heavy resources, the feedback loop between the agent and the human begins to degrade. UI stutters and log latency make it impossible for a developer to monitor 5 parallel processes in real time, effectively compounding the human cognitive limit with mechanical friction. The CMUX terminal acts as the architectural counterweight, a native macOS workstation built around composable primitives rather than a resource-intensive GUI wrapper. To maintain a zero-latency feedback loop, CMUX is built using Swift and AppCape bindings, utilizing the GPU-accelerated libghosty rendering engine to handle the environment. This lean rendering stack ensures that local resources remain available for the agents themselves, allowing the human to function as a high-speed reviewer rather than an operator fighting against interface lag. Organizing dozens of active terminal sessions on a single screen usually results in a chaotic mess of overlapping windows and buried tabs. To solve this, CMUX uses a structured 4-layer hierarchy. As this diagram shows, the outermost container is the macOS window, the primary frame for the workstation. Inside that window are workspaces. These represent persistent, independent groupings. Because they are decoupled from the OS window, a developer can move an entire workspace between monitors. Each workspace is further divided into panes, the visible split containers forming the grid. Finally, inside those panes are the surfaces. This is the leaf node where the actual work happens. Here is the architectural twist. A single physical pane can host multiple stacked surfaces via the bond split tab strip. Only one surface is visible at a time, while others run invisibly underneath. This asymmetrical model allows developers to nest dozens of agent sessions inside a fixed split layout, preventing the global interface from collapsing into visual clutter. When a background agent hits a blocker, like a test failure or a prompt for approval, the interface must route the developer's attention to that exact coordinate. Agents signal these milestones using standard terminal escape sequences, specifically the OSC 777 or OSC 99 protocols. CMUX intercepts these signals and renders a bright blue neon ring around the border of the blocked pane. It turns an invisible terminal event into a primary visual cue. Simultaneously, the vertical sidebar tracks the unread state. It displays unread badges, parses the current ape branch, checks the linked PR status, and monitors open listening ports. This gives the operator an at-a-glance status board for every agent in flight. To manage this queue, developers use a keyboard-addressable triage system. Pressing Command-Shift-U instantly focuses the workstation on the most recent unread agent. Command-Control-U allows the user to cycle sequentially through all unread workspaces, operating much like a focused email inbox for active code changes. These semantic UI features transform agent logs from a stream of text into an actionable, keyboard-driven triage queue. For an agent to be truly autonomous, it needs to be able to manipulate the terminal layout just as a human would. CMUX enables this through a Unix domain socket, an ultra-low latency backbone for inter-process communication. This diagram shows how data travels from an isolated CLI agent directly into the application's command pipeline. When an agent starts, CMOX injects specific environment variables, like the workspace ID and surface ID, directly into the shell, giving the agent spatial awareness of its exact location. This awareness allows for recursive orchestration. A primary agent can send a CMOX new split command through the socket, triggering the UI to physically split and spawn a secondary teammate process. The orchestrating agent then uses CMOX send to dispatch specific instructions directly into that new subpane's input stream. While the teammate works, the primary agent monitors the progress by executing CMOX read screen, evaluating the output to determine the next step. This entire coordination loop happens locally. It requires no external message queues or APIs, relying purely on the terminal's programmatic primitives. Exposing core UI controls via Unix sockets allows agents to autonomously organize their own workspaces and manage complex multi-agent workflows. Text-based environments fail when an agent needs to verify visual changes on a dev server or interact with a rendered UI. CMOX solves this by embedding a native WebKit browser panel directly into the terminal layout. Unlike a background, headless Chrome process, this browser is physically visible to the human supervisor. Using the CMOX skills library, agents can programmatically snapshot the accessibility tree, inspect the DOM, and execute clicks or form fills. Because the browser lives adjacent to the terminal pane, the agent operates in the same visual context as the developer, allowing for immediate visual verification of its work. Testing web servers also requires safe file system access. If multiple agents modify a single repository checkout simultaneously, they will inevitably overwrite each other's work or break the build. Get work trees resolve this by isolating branches into separate directories without duplicating the underlying Git database. Commands like CMOX new and CMOX start wrap this logic, automating the creation of isolated branch checkouts for every agent session. By combining adjacent WebKit rendering with strict worktree isolation, agents are given a safe, fully contextualized environment to execute complex development tasks. These advanced orchestration capabilities change how we view the role of the legacy multiplexer. A tool like tmux is engineered for server-side persistence across network boundaries. CMOX is a native macOS application built for local UI management and agent communication. The most effective professional setup involves using both, running the CMOX UI locally while attaching to persistent tmux sessions on a remote host via SSH. This configuration allows heavy AI inference to run on private infrastructure, while the local machine handles the semantic notification routing and visual triage. This aligns with the primitives over prescriptions philosophy. CMOX provides the building blocks, the sockets, the browser, and the notification system, and leaves the workflow to the developer. Community-built extensions can then coordinate these primitives into robust task distribution systems using simple shell scripts. Moving core terminal controls into a scriptable, semantically aware control plane provides the necessary infrastructure to supervise autonomous AI at scale.